Hello, this is going to be the second part of the Laplace transform operational properties section. And this is to get some examples where we're using all the shifting that we learned on some IVPs. Okay, so we can handle a wider variation of problems. So we're going to use the Laplace transform to solve the given IVP where we have y prime minus 2y is 3 plus t e to the t, and y of 0 is equal to 0. So this is just a first order problem to get our feet wet, kind of. And so here we go. We take the Laplace of the differential equation. We get the Laplace of y prime minus 2 Laplace of y equals the Laplace of 3 plus the Laplace of t e to the t. The Laplace of y prime, I wanted to show you all this because this is also in your Laplace transform table. We have the general form right here. So that's for an nth order derivative. And so for the case where n is equal to 1, we're using f prime of t, and we're looking at the Laplace. It's going to be, well, n is 1, so that's s, big F of s, minus s to the 1 minus 1, that's s to the 0 times y of 0, little f of 0. And since our powers of s are already gone, we can't go any further, so this is simply s, big F of s, minus little f of 0 for the initial condition. And so that's how you use that table. Okay, so let's go ahead and use it now. Laplace of y prime, that will be s, big Y of s, minus little y of 0, minus 2 times the Laplace of y, which is big Y of s, equals the Laplace of 3 is 3 over s, and then plus the Laplace of t e to the t. I see an exponential multiplier. That means I'll have a shift in the s world. So this is the same as looking at the Laplace of t, and then on the outside we'll have where we evaluate s at f of s and take it to s minus 1. Okay, so now substituting some values in here, I can see the y of 0 is equal to 0. That's our initial condition. On the left, I can factor out a y of s, so I have s minus 2 times big Y of s. On the right, I have my 3 over s. And then my Laplace of t is going to be 1 over s squared, but that s squared has to go to s minus 1. So this is going to be plus 1 over, in quantity, s minus 1 all squared. Okay? Now, the next thing to do, there are a couple of things. I think first, on the right-hand side, I should get a common denominator. It is always better to do one partial fraction decomposition than it is to do two. So I don't want to keep these as two separate functions or fractions. I want to have just one. So the common denominator would be 3 times s minus 1 all squared plus s over s times s minus 1 all squared. I'll have to FOIL out the numerator, and that's fine. But now, when I get my y of s by itself, I get y of s is equal to, in the numerator, I have the s minus 1, which is s squared minus 2s plus 1. So that's 3s squared. The minus 2s times 3 gives me minus 6s. The plus 1 times 3 is a 3. And then I have a plus s all over s times s minus 1 all squared times the s minus 2. And this finally simplifies fully to be 3s squared minus 5s, write your 5's and your s very distinctly, plus 3 all over s times s minus 1 squared times s minus 2. Okay, so that's written as simply as I can possibly write it. Now I do a PFD. So we're looking at breaking down 3s squared minus 5s plus 3 over s times s minus 1 all squared times s minus 2. I have 4 factors in the bottom, so I expect there to be 4 fractions. All the factors are linear, So all the coefficient, or all the numerators should just be coefficients. I have a over s plus b over s minus 1 plus c over s minus 1 all squared plus d over s minus 2. Okay, now what I do is I clear the fractions. I have 3s squared minus 5s plus 3 equals a times s minus 1 all squared times s minus 2 plus bs times s minus 1 times s minus 2 plus cs times s minus 2 plus ds times s minus 1 all squared. It looks like we can do the same trick where we let s take on values to simplify our work. So the wise ones for now are s is 0, 1, and 2. So I'll let s equal 0 first. On the left-hand side, 3 times 0 minus 5 times 0 gives me 0, so I just have a 3. And that's equal to, looks like the terms with b, c, and d would all go to 0, so I'm only focusing on the a. Plugging in s equals 0, I have a negative 1 squared times a negative 2. And so this means 3 is negative 2a, or a is negative 3 halves. Then I let s equal 1. On the left-hand side, I get 3 minus 5 plus 3. On the right-hand side, the terms with a, b, and d in them all go to 0. So I'm looking at the c term. So c times 1 times negative 1. On the left, I have 6 minus 5 is 1. That's equal to minus c. So c is a negative 1. Next one is to let s equal 2. On the left-hand side, I have 3 times 4 is 12, minus 5 times 2, that's minus 10, plus 3. That's equal to, looks like a, b, and c will all go to 0, so we're focusing on d times 2 times 1 squared. We have 15 minus 10, which is 5 on the left. That's equal to 2d. So d is 5 halves. And then last, I need to pick any value of s that would be helpful. A nice one to use is s equals 3. I don't want to use fractions. And I don't really like to use the negative numbers. So 0, 1, and 2 are already taken. That's why I chose 3. Nothing really strategic about it other than some laziness. That's why I don't want to use fractions. And more chances for error if I use negatives. So I'll just focus on s as 3. When I plug in 3 on the left, I have 3 times 9, which is 27, minus 15 plus 3. On the right, I have a times, plugging in 3, I get a 3 minus 1, which is 2, all squared is 4. 3 minus 2 is 1, plus b times 3, 3 minus 1 is 2, and 3 minus 2 is 1. I need to kind of move these over a little bit. Hang on. And then for the c's, I have plus c times 3, and then 3 minus 2, that's just 1. And then plus d times 3, and then the 3 minus 1 is 2, all squared is 4. Okay, let's simplify that. On the left, I have 30 minus 15, that's 15. This is equal to 4a plus 6b plus 3c plus 12d. I am trying to solve for b. Okay, so I'm going to plug in what I got for a, c, and d. 15 is 4 times negative 3 halves plus 6b plus 3 times negative 1 plus 12 times 5 halves. Simplifying the fractions, I get 15 equals negative 6 plus 6b minus 3 and then plus 30. So it looks like on the right, I have 30 minus 9, so that's 21. So I'm going to bring it over. 15 minus 21 is 6b, and 15 minus 21 is going to give me a negative 6. So this means b is negative 1. So I have all of my numerators here. I can plug them in, and then I can go ahead and say that our little y of t is going to be the Laplace inverse of a over s, so negative 3/2 over s, plus b over s minus 1, so that's minus 1 over s minus 1, plus c, which is minus 1 over s minus 1 all squared, and then plus d, which is 5/2 over s minus 1 all squared, or sorry, s minus 2. Okay. Aside from any arithmetic errors, that is always a thing that could be happening. This is our process here. And so now when we go to take our Laplace inverse, one thing that we really want to take note of is where there's a shift, right? So we've got this shift where we have this s minus 1 all squared. That one is the one we have to worry about. The rest of them, they seem fine. They're like, I can go straight to the table and figure them out. So what I get here is the first one, minus 3/2 over s. That gives me a minus 3/2. The Laplace inverse of 1 over s is just going to be 1. The Laplace inverse of 1 over s minus 1, this gives me a minus e to the t. And then the next one, that one's going to give me, so I'm dealing with Laplace inverse of 1 over s minus 1 all squared. This is going to give me minus the e to the t, where t has to go to, hang on a second, hold on, how do I want to write that? I have my shift, my e to the t, and then, sorry, it's the Laplace inverse of 1 over s squared. That's how we do it. Okay, so we get our multiplier, and then we can focus on the big Laplace inverse of big F of s without the shift. Then finally, plus 5/2, and I'm dealing with 1 over s minus 2, which is just going to be e to the 2t. Okay, and then one more fix here, or one more thing to do is the Laplace inverse of 1 over s squared is just t. So finally, this becomes minus 3/2 minus e to the t minus t e to the t plus 5/2 e to the 2t. And then we're done. Okay, so the only places where things were different was right in the beginning when we took the Laplace of t e to the t and we had that shift. Okay, and then at the end, when we had the s minus 1 all squared, and we had to remember, oh, we're going to have to shift that as well. But I want to draw your attention to the Laplace transform table. And we're going to go back to the first page, possibly the second page. Here we go. I want you to pay attention to 16, and in fact, 17. I'm a big fan of using the table for its power, and we already have the Laplace of t e to the at figured out. We also have the Laplace inverse of 1 over the s minus a all squared figured out. So I think it's good to learn the technique, because in a future class, like in an engineering math class, you may be expected to be able to figure it out without using the table. And so, well, if you know it from first principles, you'll be okay. I'm okay with you using the table, so long as you're citing that you're using the table, okay? All right, let's go back. Okay, next problem. So we have to use that unit step function for its power, and We're going to use it when we've got a differential equation that is equal to some random f of t, where f of t is a piecewise function. So this is saying that our differential equation is equal to some non-homogeneous term for different t values. That's a little weird. So we need to rewrite, that's going to be our first job, we need to rewrite f of t as a sum of functions. Otherwise, we won't be able to handle this, because I don't know how to take the Laplace of a piecewise function, but I do know how to take the Laplace of a unit step function. So I'm going to use that. So first things first, we need to figure out f of t. F of t is equal to first 2, right? It's equal to 2 in the very beginning up until t equals 1, at which point we have to shut it off. So we do minus 2 u of t minus 1 to shut it off. Then we turn it on again. But when we turn it on, it's plus t, and it starts at u of t minus 1, and then it goes on like that forever. It doesn't shut off again. And so this is our function. I can simplify it a little bit more. This is equal to 2 plus, in parentheses, t minus 2, u of t minus 1. Okay. So that means our differential equation, E was hard to write. Our differential equation is y prime minus y is equal to 2 plus, in parentheses, t minus 2, u of t minus 1. Okay. Now, I can go ahead and take the Laplace of both sides. So the Laplace of y prime minus the Laplace of y is equal to the Laplace of 2 plus the Laplace of t minus 2 u of t minus 1. Now I want to make a point here that a is equal to 1. And we have f of t is equal to t minus 2. Let's find f of t plus 1. So everywhere there's a t, plug in t plus 1, and we still have the minus 2, and this becomes t minus 1. Okay? So on the left-hand side, the Laplace of y prime is s, big Y of s, minus little y of 0, minus the Laplace of y, which is big Y of s. That's equal to the Laplace of 2, which is 2 over s. And then from the Laplace of a unit step function, we are going to get a exponential multiplier, e to the minus as. A is 1, so it's just e to the minus s. And then we're going to be looking at finding just the Laplace of t minus 1 based on, well, let me show you which one I'm using again. I'm using 57, this one right here. Okay, so instead of trying to rewrite f so that it's got the same shift as u, I just go ahead and use 57 to make it a little bit easier on myself, a little more direct. Okay, on the left-hand side, y of 0, our initial condition y of 0 is 0. And so we simply have, in parentheses, s minus 1 times big Y of s is 2 over s plus e to the minus s times the Laplace of t is 1 over s squared minus the Laplace of 1, which is 1 over s. Okay, all Laplaces have been taken. I should rewrite the right-hand side so that the stuff inside of the parentheses has a common denominator. So I get 2 over s plus e to the minus s times 1 minus s over s squared. Okay, now divide both sides by s minus 1, and y of s is equal to 2 over s times s minus 1 plus e to the minus s times 1 minus s over s squared times s minus 1. Now what you have to recognize is when you have common factors between the numerator and the denominator. 1 minus s over s minus 1 is equal to a negative 1, because 1 minus s is a negative of s minus 1. Okay, so I'm going to rewrite one more time. Y of s is equal to 2 over s times s minus 1 plus e to the minus s times negative 1 over s squared. So the e to the minus s multiplier with the negative 1 over s squared, I have a simple function right there. I don't need to do a partial fraction decomposition on it. But the 2 over s times s minus 1, I need a partial fraction decomposition. And so when I do that, I'm dealing with 2 over s times s minus 1 is a over s plus b over s minus 1. If I clear the fractions, I get 2 is equal to a times s minus 1 plus bs. Then I can let s equal 0. I get 2 is equal to a times negative 1 plus b times 0. So a is negative 2. Then I can let s equal positive 1. And I get 2 is a times 0 plus b times 1. So b is 2. So finally, what I have here is y of t is equal to Laplace inverse of big Y of s, which will be the Laplace inverse of the sum of all these terms. So I have a negative 2 over s plus 2 over s minus 1 plus e to the minus s. Let me rewrite that as minus e to the minus s times a 1 over s squared. Okay. Now, the first two terms are pretty direct. The Laplace inverse of minus 2 over s is just minus 2. And then plus the Laplace inverse of 2 over s minus 1, that's just 2e to the t. And then dealing with the minus e to the minus s, so I have a minus sign, and I know that I get a u of t minus 1 from that exponential multiplier. And then I also get a t. The Laplace inverse of 1 over s squared is t, where t has to go to t minus 1. We have to get that shift, okay? And so our final answer will be minus 2 plus 2e to the t minus, in parentheses, t minus 1 times u of t minus 1. Okay. So these two examples brought up each of the shifts in slightly different ways. Every problem will be nuanced in a different way. So you want to do plenty of problems to get comfortable with these. And, you know, if the assignment that's in WebAssign isn't quite enough, I'd say open up the book and try some more problems in there. And as always, if you have any questions at all, please feel free to reach out.